Welcome back to Calculus. In the last video, we saw an algorithm for finding all the local maxes and mins of a function, and it had these two steps. So remember, we first find all the critical points. A critical point is an x value where the derivative of the function is 0 or undefined. So you've got a horizontal tangent line or just no tangent line, no well-defined tangent line. And then the second step was, well, you've got this list of critical points now. That's the only places the max and min can occur. So then you just check each one, and if you've checked all of them, then that's everything, right? Because Fermat's theorem says that's the only things that can happen. But I didn't go into any detail about how do you check. So this video is about, now that you've got this list of critical points, how do you actually check each point, okay? So let me draw you a couple pictures and show you how this might work. There are actually two different ways to check. This video is about one of them. There's another video about another one. The first one we're going to learn is called the first derivative test. And basically, we can examine the function using either the first derivative or the second derivative. And when we use the first derivative, that's called the first derivative test. And when we use the second derivative of the function, that's called the second derivative test. So let's look at the case where we have a local max and see what might be happening with the derivative. So a local max, remember, can look like this. You've got this point C here. That would be your critical point. Or you could have a local max, maybe something like this, where the derivative is undefined, and you could have that as your critical point. But the thing we want to realize is, what is the derivative doing not at C? We know what the derivative is doing at C, right? It's 0 or it doesn't exist. But what about before and after? So if we look at the derivative a little bit before C, this says, well, f prime is increasing towards the maximum, right? So here, f prime is positive, and after the maximum, the function has to be going down, right? It can't keep going up after the maximum. So over there, on the right side, f prime is negative. And the exact same thing happens in the does not exist case. Before the critical point, f prime is positive, and after the critical point, the function is decreasing, so f prime is negative. Okay, cool. Well, let's compare that to a local min. So now we have a valley, if you will. Something like this, if the derivative exists at C, so the derivative is 0 at our critical point. Or we might have the derivative just not exist, and we get a minimum that way. And now if we look at the first derivative, on the left side, f prime is negative because the function's decreasing towards that minimum. And on the right, f prime is positive. The function's increasing after the minimum to get bigger. Okay, and the same thing happens in the does not exist case. So on the left, f prime is negative, and on the right, f prime is positive. Cool. So this gives us a way of using the first derivative to detect which of these situations we're in, whether we're in the local max situation or the local min situation. Okay? And when we do that, it's actually a theorem, and it's called the first derivative test. That's kind of the proof, though, is that picture there. So I didn't want to write all this by hand. Hopefully you're okay with that. You can pause the video if you want to write it down. So the first derivative test says you have a critical point. An important thing about this is you do have to assume the function's continuous. You could have a critical point where the function is not continuous if you have a jump discontinuity and the derivative doesn't exist there, but let's not worry about that right now. Usually your function's continuous. And then if your derivative changes from positive to negative, you have a local max. And if the derivative changes from negative to positive, then you have a local min. Okay? And that change could be because the derivative goes through 0 or because the derivative is undefined. So you don't need to memorize this. You really don't. What you should memorize is the picture. So local max looks like this. Local min looks like this. That's what you really want to remember. And you can just look at the picture and say, oh, to the left, say in the max case, I'm right here. To the left, f prime is negative. And to the right, f prime is positive. And I don't actually have these statements like memorized by heart or anything. I just remember the picture, and that is good enough because that's actually how it works. Okay, so yeah, it's pretty useful, right? One thing I should note here is that what happens if you don't have a max or min? So what if you have something like this? This, I guess, technically isn't part of the first derivative test. But what if I have a function, kind of like my old friend x cubed? My critical point is there. Well, on the left, f prime is positive because the function's increasing. And on the right, f prime is still positive because the function is still increasing. So the derivative just kind of bounces off the x-axis without changing from positive to negative. So if, this is not actually part of the test, but it is certainly true, so I'll just put this as a note separately, I guess. If f prime does not change sign, so the sign of a function is whether the function is positive or negative. So if prime does not change positivity or negativity, change sign, at x equals c, then the function doesn't have a max or min there. And you know, now that I'm thinking about it, I should really try to be a little more precise with this. So if you have a function that's like a horizontal line, it's not changing sign, and the function does technically have a local max or min. But yeah, just if your derivative's not identically 0, let's say. That's the really weird case. So I should make that exception, but really we don't worry about that too much. It doesn't really come up, right? If you have a constant function, you don't really need to use a lot of fancy tools to investigate it. Constants are pretty easy to understand, even without calculus. Okay, so let's try an example. Yeah, what if, here's the sort of phrasing you might see on your exam or maybe on your homework or something. Let's find and classify all the local extrema for this function. So let's just start out with a not too difficult one. So we'll say 2x cubed plus 3x squared minus 36x. So good old cubic. If we had a quadratic, that would be too easy, right? Because a quadratic just has that one max or min, and you don't even need calculus to find it. You can use the vertex formula or other tools. But a cubic, now you really kind of need calculus unless you're going to use technology or something. Okay, so what are we going to do? Well, there's those two steps, right? So step 1 is find all the critical points. Remember, those are points where the derivative is undefined or where the derivative equals 0. But for this function, it's polynomial, so the power rule and the constant multiples and the summation rules say that we can differentiate this and get another polynomial, and that's going to be fine everywhere. So the derivative is going to exist everywhere, so we just have to look for where f prime is equal to 0. So what I'm going to do is find f prime of x. That's a pretty simple one. Now we've been practicing this for a while, so we've got 6x squared plus 6x minus 36. So there's my derivative. And then I need to set it equal to 0. Okay, so this is finding the critical points. That is step 1 of my algorithm. Before I can classify anything, I need to know which points I actually have to classify. So find the critical points first. And let's see. I guess I'm going to factor out a 6. That seems like a good thing to do. And then I know how to figure out where a polynomial is 0, right? I factor it. So I'm going to say x minus, I guess, what multiplies to 6, to negative 6 and adds up to 1? I guess I'm going to do minus 2 and plus 3. That seems like a good plan here. You can check that in your head or on paper, I guess, if you're not sure, but pretty sure that factors. Okay, which tells me that f prime of x equals 0 when x equals negative 3 or x equals 2. All right, so these are the critical points. This is step 1, list of critical points. I guess I can write it out explicitly here. List of critical points is x equals negative 3 and x equals 2. Okay, so now I need to classify them. So that is step 1 of my algorithm, make a list. Those are the only possible places that my function can have a local max or min. So if I don't know what's happening at x equals 12, that's fine. I know it's not a max or min, because the max or min can only happen at these points. Now I need to know, does a max or min actually happen at each of these points, and what kind is it, if there is one? So that's what the first derivative test is for. So let's make a note. This is how we actually use the first derivative test in practice. A continuous function cannot change between positive and negative I could say change sign, I guess, between positive and negative without going through 0. That is the result of a theorem that we don't get to prove or really even investigate in detail in this class, but it's called the intermediate value theorem. If a function goes from like -1 to +1, it has to take all the values between -1 and +1, and that includes 0. So we can't change sign unless going through 0, and we know that x equals -3 and x equals 2 are the only places where the function equals 0. So what I'm going to do is I'm going to draw a number line. This is kind of like when we were graphing earlier. So I'm going to put -3 and +2 on the number line. And what I need to do is I'm going to choose a test point. I guess I want f prime still on here, but I'll just write it again. I want to choose a test point for f prime in each interval. Let's say each subinterval. So these critical points kind of divide up the x-axis into regions where the function is increasing or decreasing. So if I know everywhere between -3 and -2, so everywhere on this entire interval here, the function is always increasing or the function is always decreasing. It can't do like some increasing and some decreasing between -3 and 2, because if it changed between increasing and decreasing, it would have to hit 0, and we know it doesn't hit 0 anywhere inside that small interval. It only hits 0 at -3 and 2. And on the left side of -3, the derivative has to always be the same, always positive or always negative. So if I just test a single point on each interval and plug that into the derivative, that tells me what the derivative is doing, not just at that point, but on the entire subinterval. So you can pick however you want to choose your points. In between -3 and 2, I'm going to pick 0. So I'm going to plug in x equals 0. To the left of -3, I would probably pick -4. And to the right of 2, I would probably pick 3. So I just pick points that are easy to plug into the derivative. Okay, so let's recall what the derivative was. I'm going to use the factored form of the derivative. F prime of x was equal to x plus 3 times x minus 2. And I guess there is actually a 6 out in front if I want to be precise. Not that the 6 is really going to matter here. But, okay, so I need to know for each of these points, -4, 0, and 3, is my f prime positive or negative? And I only need to test those points. So you could plug in and do a calculation, but you don't really even have to do that much work. So I don't care about the actual value of f prime of -4. I just care about whether it's positive or negative. So I'm going to take 6, and then I'm going to do -4 plus 3. I don't care what value that is. All I know is that that is a negative number. Right? So -4 plus 3, that's negative. -4 minus 2 is negative. What is 6 times a negative number times a negative number? That is a positive number. Which means that at -4, the derivative is positive, and everywhere to the left of -3, f prime is positive. Okay, so that single test point tells me about every point to the left of -3. And again, I don't care about multiplying them out and getting a specific positive number. I just care that it's positive. Okay, so let's do f prime of 0. That's going to be 6 times, now when I plug into the x plus 3 part, that's going to give me a positive number. It's actually positive 3, but I don't care what it is. When I plug 0 into x minus 2, that's going to give me a negative number. So the result is a positive times a negative, and that is negative. Which means that in here, f prime is negative. Okay, and then finally, we'll look on the right, so we'll do f prime of 3. we get 6 times, let's see, 3 plus 3 is positive. 3 minus 2 is positive. Positive times positive is positive. So over here, f prime is positive. Okay? Okay, so now I'm going to look at my number line, and I'm going to say, by the first derivative test, at x equals -3, the derivative changes from positive to negative, which means my function goes from increasing to decreasing. So f has a local max. And at x equals 2, it's the opposite. Goes from negative to positive. So at x equals 2, so I'm looking way up here, up at this part here, my function changes from negative to positive. So the function, the derivative changes from negative to positive. The function goes from decreasing to increasing. So f has a local min. By Fermat's theorem, we can't have local mins or maxes anywhere else. They have to occur at the critical points. So I have found all the critical points, which means I found all the local max and mins, and they are classified. Okay, so that is a full run through. We'll do some more examples in another video, but I think that's enough for now, and I'll see you next time.